Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 40, gases part 6. This is the last video in chapter 5. Here are our objectives for today's video. Pause here. So we spent this entire chapter talking about ideal gases, and today we're going to talk about real gases. So these are pretty much every gas can be classified as a real gas, but we're going to call most gases ideal, and I hope that that's clear by the end of this discussion why we do that. So a real gas, they are not so small that the volume is negligible, and they do experience intermolecular forces. And what that means is that PV equals nRT doesn't 100% work, and we're going to need to make some corrections to it, only if we're working with experiments that we really need that degree of sensitivity. Pause here. So this is the van der Waals equation, which it really is just PV equals nRT with some correction factors. So OBS, that means observed. So observed pressure, which is going to be different from PV equals nRT. So observed pressure plus A, this is just a constant. Each gas has its own value of A and B. You need to be given what they are, times moles over volume squared, times V. But then we have this correction factor NB is equal to nRT. Again, every gas has their own values of A and B, depending on how much they interact with other things, meaning how strong of intermolecular forces do they have, and their radius. Pause here. Right. So the first correction factor that we have, you don't actually need to write down that equation. Some students get confused by it, by the way. So the first correction factor, and what I've written here is only true if A is equal to 0. They are not so small that their volume is negligible. Real gases, because of the fact that the gas molecule itself takes up some space, their volume, meaning the empty space, is going to be a little bit less. So the higher the value of B, the larger the atomic rate or the molecular radius of the gas particle. Pause here. All right, I'll say the answer out loud in just a couple of seconds. Right, so the higher the value of B, the higher the pressure. So mathematically, you're taking the denominator of an equation and decreasing it. So that's why. But also conceptually, if I have less space in a container, that means that gas molecules are going to hit those sides of the container more, which will increase pressure. Pause here. Then we have our second correction factor, which is the A. So this accounts for the fact that there's going to be intermolecular forces. So the higher the value of A, the higher the intermolecular forces. Pause here. So I don't typically assign these on tests, but I wanted to work through one of these with you so that you can see what this would look like. So the first thing I'm going to do is I'm going to actually take the equation, the van der Waals equation, and I'm going to rearrange it for P observed. I'm going to work through this. The sig figs for this can be admittedly a little annoying. Okay, so now I'm going to do this step by step. So the first thing I do is I take care of this. I multiply this out, and I get 0.0171. The next thing I do is I take this factor here and I multiply it. I'm going to round it to 3 significant figures because it's just multiplication here. Next thing I do is I take care of my subtraction in my denominator here. Next thing I do is I take my first part and I multiply this out, rounding to 3 significant figures. And then I do my subtraction. And so that was a lot of work just to get 1 ATM. The point that I'm making here is that these differences are so small. The difference mathematically between a real gas and an ideal gas is so small that it's almost never going to be worth it in a lab context to use this equation. But the equation is useful to help us understand the differences between real and ideal gases. Pause here. I'll say the answer out loud in a couple of seconds. Gases behave most ideally at high temperatures. There's a lot of ways you could think about it. The easiest way I can think about is at low temperatures, a gas often becomes a liquid, which is the opposite of an ideal gas. I think that's the easiest way to think about it. Mathematically, the effects of A and B are less profound at higher temperatures. And also at higher temperatures, things are moving faster, so the effects of intermolecular forces are lower. You don't have to use all 3 of those things. You could pick the one that you like the most, but the higher the temperature, the more ideal something is. Also, the lower the pressure, although the question wasn't asking for that. Hey, thank you so much for watching and have a great night.